this is Seth Juarez, and I'm here at the Microsoft Research Faculty Summit 2015, and I'm here with these two distinguished gentlemen. Let's start with the first thing, computational rationality. I've heard that term before. What does it mean from the cognitive psychology perspective and then from the machine perspective?
For me, there's sort of three components to this idea that are really in common. I see them as representing a kind of a synergy or a synthesis, a convergence of ideas in cognitive science, in AI, and also to some extent in neuroscience. And to me, those three ideas are, one, the idea that we can understand intelligent behavior as a certain kind of rational action. But I think coming to both of us is an idea that maybe you could associate with like the foundations of economics and the mathematics of probability, the idea that intelligence is something about forming beliefs and using those beliefs to achieve your desires, and then formalizing beliefs and desires in terms of the mathematics of probability and utility theory. But then there's the idea that if you're going to build an intelligent agent, either artificial or natural, that tries to, has its overarching goal to maximize expected utility in the real world for the kinds of problems that confront us, that is incredibly difficult. And then there's this third idea that you want to be smart and even rational about how you approximate your rationality.
In the 20th century saw some really interesting thinking that went on outside the realm of computability or computation. And one theory for what one does in a complex world where we as people or a machine as an agent is uncertain about what's going to happen, what the world looks like. In considering actions, there's a model of ideal action to take that came out of theoretical foundations of what was called utility theory. And over the decades, there was a bifurcation early on in AI because it didn't seem those formal models could be computed very easily. Where do the probabilities about different states of the world come from? What's the objective function? How do you compute these things with the scarce resources we had to compute? And so some of the interesting motivating work that came out of the 1950s and 1960s and 70s looked at bounded rational systems that couldn't possibly, from the point of view of the designers, do the right thing, collect enough evidence or information to be rational. And there was kind of a discarding of that whole viewpoint. It was, think about machinery that helps a person get through life with heuristics. What works well? What are some patterns of logic that might be useful? What kind of patterns might be matched in a very, very ad hoc way, you might say? But what happened in the 80s, late 80s, was the rise of interest in science of bounded rationality. And the way Josh and I look at this is, what happens when you put a computational lens on scientific theories of rationality? You start saying, well, listen, I need to come up with certain kinds of approximations. I need to, offline or in real time, have a layer that reflects about how to do things, because I can't do it all. And even have to worry about how complex that is in itself. And then I need to sort of learn and figure out where I put resources of various kinds, collecting information, collecting data, thinking more.
Is there evidence in human cognition that that's how humans behave? That they have this fast model and this slow model, and they actually decide when to use either or?
I mean, it's through some combination of evolution and early development. In some sense, our vision is something we're heavily optimized for, right? And the trade-offs of how you combine the fast bottom-up system and the slower top-down model-based system. In some sense, evolution already, the meta-rationality there is done by evolution. But then there's things which are more like what we think of as thinking, right? Like planning, like deciding, okay, how am I going to get, when I wake up from where I was staying last night, how am I going to get here today? Am I going to drive down the highway, or am I going to take the slow route?
Does the human mind operate in a way that at times will resort to richer, slower, potentially more precise or less familiar situations in a more computationally intensive way, versus sometimes flipping to a quick reflex and recognition, for example. And I think there's evidence, and people have been studying in psychology and have results along these lines, that there are some fast twitch and slow deliberative systems, and it's unclear, what
Yeah.
all the machinery is that guides these.
I mean, you can see this in navigation, though, right? I mean, like, because when sometimes you're just sticking to the routes that you know, and other times you actually have to stop and think and look at a map and plan and think about, is there going to be more or less traffic? So I mean, that's one example which has been studied in humans and other animals, and there are different brain systems. There are some systems which, some parts of the brain which really do a kind of planning.
Many people, core AI researchers,
Yeah.
researchers that say, I want to do artificial intelligence and make that my career, are foundationally motivated by mysteries of the human mind that they find within themselves, within people they work with, even their pets, the vertebrate animals we have in our homes are just incredible. And if you study physics or biology or chemistry, there's often a huge gap to explaining what is going on with the mysteries of the human mind. It's clearly a biological system, but we have very little understanding from the point of view of the foundations. That was true for me early in my life, where I went off to neuroscience and biophysics into neurosciences, but quickly said, I'm going to go computational because I think that that's the best path to figuring things out. And someday, and I thought, it might be 100 years, it might be 1,000 years, I want to come back to the mysteries of mind, should I not understand them yet through computation, and come look at human minds and other vertebrate creatures that have naturally evolved. It's unclear as to when the reentry for an AI researcher would be to look at results from cognitive psychology. And we think,
that's the claim.
We both think now.
Yeah.
Like now, there's a two-way, and it's not one way. It's a two-way street.
Yeah.
Where the prospect for a unifying vision, and one that we propose as one potential perspective, is one of computational rationality, where we have systems, whether they be human or biological, I should say more generally, or machine, are grappling under great uncertainty. They're trying to do the best they can. There is some representation of belief or likelihood in the world, and there's some notion of an objective function, something that's cared about over time, and all sorts of limitations in resources, the ability to think, how much time there's left before you need to make a decision, cost-benefit trade-offs in timely action versus delayed action in the world. And we can maybe understand both the biology and the computation as a broader computational framework. We'll call it computational rationality.
So to finish up, 30 seconds, future of AI, each of you.
I view AI as kind of the crest, or the crashing crest of the wave of computer science. So you look at how much computation has done for our society, for socioeconomics, in applications like healthcare, the broader biomedical sciences. It's been incredible. AI, where we're doing more and more of the things people consider only smart people could do, will change so many things. With that comes a lot of hope, a lot of possible benefits, and also some concerns with potential disruptions of a variety of kinds. Will this technology remove different whole sectors of jobs in the future? Will these machines become so powerful and smart that they can't be turned off and they come to outwit man? I think these are important and interesting questions that need to be solved along the way, but I expect largely positive, beneficial results coming out of this research, largely because we guide it. This technology is in the hands of humans, and we guide the technology.
I think if we've learned anything from the past history of AI, it's that trying to predict the future history of AI is kind of a losing game, right?
Yes.
It's hard to know where you're going or how long it's going to take, or even when you'll know that you've gotten there, right? But I think, looking both at the past and what we see going on right now that's most exciting and next steps, again, I'm sort of an optimist about these things. I'm not going to make predictions about what we're going to get to when, but this idea that AI is both an engineering discipline and a science, or you might think of it as providing a lot of the technical foundations behind the science of how the mind works, right? There's sort of artificial intelligence and there's biological intelligence, and I think we've learned this a few times now, and I think what I hope is that we've learned it in a deeply internalized way that will stay with us through the future. Is that these fields have a lot to say to each other, and that if we keep them in register, right? If AI researchers keep looking at biological intelligence for inspiration about the problems to solve and the kinds of solutions, and if the people studying biological intelligence keep looking to AI and engineering for the tools and the language in which to form their theories and to think about their experiments, right? Then I think that's going to be a really productive synergy that can take us to many interesting places.
Well, this is awesome. Thanks so much for
Okay.
spending some time with us. Thanks for watching, and we will catch you next time. Take care.
Okay.
Great, thanks.